Okay, assalamu alaikum. We're starting our class now. Last time our subject was logical equivalence, and we stopped, I think, until we take some example to prove logical equivalence. Now we will continue. Okay, then last time our subject was tautology and logical equivalence. This subject, we defined tautology and logical equivalence, and we mentioned that tautology, it's a compound proposition that always true. This means if we have a proposition or compound proposition that always true, or in another term, that logically equivalent with true, we call this type of compound proposition tautology. Okay, we take example here for P implies Q and Q implies not P, and we said this two compound proposition is logically equivalent. Why? Because when we look to the truth table for both proposition, we will find the same table here. Okay. We take another example here. There is one student sent me this question by email. He asked about this truth table, and he mentioned that he did not understand it. So I will describe it, but before that, let me check some thing with you. Okay. To use truth table to prove something, you need to understand first what is a truth table. I will use a whiteboard. Okay, imagine we have two propositions, P and Q. To use the truth table to prove any compound proposition, or to get the value of any compound proposition, for example, P implies to Q, you need to understand what we are doing. First, we give assumption here what all values could be for P and Q. P and Q propositions. This means this proposition could be true, could be false. So all the possible values for Q and P, that P could be true and Q at the same time true. Another option that P could be true and Q false. Is there other possibilities? Yes, we have another possibility that P could be false and Q true, and P and Q could be both false. This all possibilities for P and Q. So to make any proof using truth table, if we have two propositions, we will make a truth table like this for all the possibilities. Then we find the compound proposition for each of these possibilities to find its value. For example, P implies Q. What's the rule of P implies Q? The rule that if P and Q true, then P implies Q will be true. Another choice, if P, first one here, the hypothesis, okay? If P false, the result will be true. So we have two options for true value for P implies Q. If both P and Q true, this first option. The other option that if we have P, which is the hypothesis, the first term here, before the implication, if its value false, then the result will be true also. So true, the result will be true. If P true, the result will be false. If P false, the result for this implication will be true. Then this is a truth table for implication. P implies Q, or P then Q. Okay. Now I will return here. This is a truth table that I mentioned before. Here we have all the possibilities for P and Q. That is true, true, false, false, and true, false, true, false. This first possibility, second possibility, third, and for each possibility we get the result for P implies Q. Here, truth table for this compound proposition. To find this compound proposition, first question, what simple proposition we have? We have P and Q. That's why we need to get all possibilities for P and Q. So we make first all the possibilities for P and Q. This not Q come from Q. P, Q, and P. Then all the propositions that I have in this compound proposition is P and Q. Depend on P and Q. Okay, then what is the possibilities? True, true, false, false, true, false, true, false. Then I start with each one. Here I need P, which is here. And I have here operation or, and I need not Q, this one. Okay. This one, not the Q. also. So I will calculate not Q. Where is the Q? Here. What's the meaning of not Q? The negation or the negative of Q. When Q true, the negative will be false. When Q false, the negative will be true. And so on. True become false, false become true. Then now and only now I can get the first part, which is P or not Q. Okay. What's the rule for OR operator? OR operator like this. If you have any side true, the result will be true. If you have both sides false, then the result will be false. So what the both side? P, which is this one. Let me clear the screen here. So to find this one, which is the first part of the implication, I need P and not the Q. This is P and this is not the Q. Now I make OR operation between P and not the Q. What's the rule? If any option will be true, the result will be true. Here we have true and false, then the result is true. True and true, the result will be true. False and false, only if both sides false, then you have result false. False, or true or true or false will be true. True or true will be true. False or false, the result will be false. This is the only situation for OR operator. False or true, the result will be true. Then we get the first part. Now we need the second part. It's between this second part, it's between P and Q. Here, P and Q, and the operator will be what? And operator, the result of and operator, if both sides P and Q true, the result will be true. If any side false, the result will be false. Then here we have P and Q, and we make AND operation between them. True and true, the result will be true, because here we have Q false, we have P false, we have P and Q false, then all the remain will be false. Now we can make the implication between both sides. To get the final result, we have the implication here. What's the rule for implication? For implication, I need both sides to be true to get it true, or if this side before the implication false, also the result will be true. So we look first, if both sides true, yes, I have here, of course, the implication between which parts, between this one and this one. Here, both sides true, then the result will be true. Is there any both sides true? No. Now I start to look here in the first part. If I have false, the result will be true. here false, then the result true. Here I have true, and in another, the other side, I don't have another true, then the result will be false, false. Hopefully, this answer your question. I don't remember the name of the student, but from his question, I understand that some students have misunderstanding here. Okay, now we continue. After speak about logical equivalence, and we use the truth table to prove this logical equivalence, and I give you some exercise from our book to solve it. We continue today for some laws or rules for logical equivalence. We have a number of rules for logical equivalence. These rules, we can use these rules to prove the logical equivalence. So we have now two ways to make our proof. First way, truth table. Second way, logical equivalence rules or law. We have many laws or rules for logical equivalence. First one, De Morgan law. You need to memorize all these laws. It's very simple, but we have some laws here. You need to understand first, then you will memorize them if you understand. Morgan law have two copies or two Morgan law. We have, it's same idea for both law. Of course, this law for logical equivalent, this logical equivalent symbol. Okay, this law said that not P and Q logically equivalent to not P or not Q. This means in short term you can give this not for the whole, for the both side, but you need to flip this and to or. And if you have or, it will become and. So in another term, we call this distributive, okay? But it's not distributive law. We will have distributive law, but this means you can get this not inside for both proposition, but if it's not, it will become, if it's or, and it will become or, if it's not or, it will become and. Then this law, not P and Q, it's logically equivalent to, if you get this not inside, not P, and this and will become or not Q. If you have this, the first law. Second law, if you have or, it becomes and. Okay, we will prove this law, first law, using truth table. We can prove this law very easily. Okay, to prove this law, we need to get this part table and this part. If we have the same result, then they are logically equivalent. So let's check first part, not P and Q. We need the truth table for this proposition. Then we need to define P and Q possibilities, then make and, then make not. Okay, then we have P here and Q. We have all the possibilities: true, true, false, false, true, false, true, false. This all the possibilities for P and Q. Now we make the operation P and Q. We mentioned and operator before. What it will do, if you have both sides true, you will have the result true. If any of the both sides false, then the result will be false. So P and Q both true, then we have true. If any side false like this, then the result false. Okay, now last thing, we need to get the not for this proposition. Not means if you have it true, it become false. If you have false, it become true. So look, true become false, false become true, true become false, false become true, false become true. Then this is the logical or the truth table for first part. This one. Now we need the truth table for the second part. If they have same truth table, this part and this one, if they are the same, then they are logically equivalent. Now to find this, we have P and Q, then this all possibilities for P and Q. Now we get not P and not the Q, this not P. Here P, true become false, true become false because not. False become true, false become true. Same thing we do for Q, get not the Q, true become false, false become true, true become false, and false become true. Okay, now the final result for this compound proposition, we need to make OR operator between not P and not Q. We mentioned before, OR operator will give me true if any side is true. Then if you have it true for any side, this side or the other side true, you will have the result true. If you have both sides false, then the result will be false. Okay, then this both side, not P and not Q. Here both side false, then you have the result false. One side true, then true. This side true, then the result true. This side true, then the result true. If you look here, this result and this result, it's identical. Same. False, true, true, true. False, true, true, true. Then we proved that this compound proposition logically equivalent to this compound proposition. Then we proved De Morgan law using truth table. Same way you can prove the second law. Okay, then this De Morgan law, if not want to be distributed for and, you can distribute it, but and become or. If not, will distribute it for two proposition with or, then you can distribute it like this, but the or become and. Very simple and direct law. Okay. We have another law here, which is distributivity law. This law mentions that you can distribute and operator on or, and you can distribute or operator for the and. Both distributivity law. So you can make like this. If you have P and between brackets Q or R, R of course is another proposition. It's same like P and Q. You can have R, K, L, any other name for proposition. Okay. So you can distribute this P and Q or P and R. P and Q or P and R. Same thing, if you have or, then you can say P or Q and P or R. This similar rule, we have two distributivity rule. We can prove this rules using truth table. Same idea. We will need first part and prove it. We proved it here. And we need second part and get the truth table for it. We get it here. Then you need to check if both sides identical. If you check both sides identical, true, true, true. Just I want to mention one thing here. It's very clear how to make the proof, but we have here 1, 2, 3 proposition. Yes. So if you have 3 proposition, your truth table will be like this. Also, same idea. We need all the possibilities. If we have P, Q, R, what all the possibilities? That true, true, true. All become true. Or another possibility will be true, true, false. True, false, true, and so on. Okay, you get all the possibilities. To make it much easier for you, if you have 3, it will be 8 possibilities. If you have 2 proposition and you have true and false, this means 2, then you have 4 possibilities. Okay, if you have this number of a proposition, if you have 3 proposition and we have 2 possibilities, then we have 8 possibilities here. This 2 become because we have 2 choices, true or false. Okay, then as you can see here, we have 1, 2, 3, 4 until 8. How to write it? Simplest way. I did not understand it. Do you mean, oh, it's not distributive. Okay, Ahmed, I understand your question. Do you mean if I have P and between the brackets Q and R like this? Yes, it's not a distributivity. Actually, if you have all operator same, you can what we called it, this rule, I forget the name, but you can take each two with each other. It's normal. It's not distributivity. You can take P and Q alone, then and R. Sorry, no need for this. Or you can take P and R. It's another rule. I will mention it. But you cannot distribute it if you have both and or both or. It's another rule. Yes. Yes, yes, commutativity. I will mention this rule later, but it's another rule. You cannot distribute and with and. It's same like in the mathematics when you said x multiply by y multiply by z. It's similar because same operation. You can set x multiplied by y multiplied by z directly, or you can set x multiplied by z by y. It's similar. But if you have different operator like this in mathematics also, x multiplied by y plus z, then you have same law here, distributivity. X will be multiplied by y and z. The only different here that this operator, or no different, just you need to focus to the type of the operator here. This distributed on the practice, yes? So this in the middle and this both sides. Okay, actually, I want to make this much simple for you. How to write this value without any mistake. Okay, if you have two proposition, then the sequence will be like this: true, true, false, false, then one true, one false, true, false, true, false. If you have three proposition, it's very similar. You consider the new proposition at this part, for example, R. So you can make it like this: true, 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 true. Now you repeat all this with the false. So it become like this. If we have P, Q, and R, then we have true, 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 4 times. Then false, 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 false. Now the other one, like if we have only 2, it's become true, true, false, false, true, true, false, false. You can understand this sequence. It's like 4 times, 2 times sequence, then 1 time sequence. True, false, true, false, true, false, true, false. Like this, I can write all the possibilities for these propositions. Then you start the proof. I need here P and R. I need P. We prove this one, I think. This one, number 2, not number 1. So we make Q and R. Then we make Q and R here, which is here, or P, to get this side. Then we get the other side. Same way, we need P or Q, P or Q, then P or R, P or R. Then we make and between this both sides. Okay. Okay, sorry. This this law which is contrapositive law, mentioned that if I have P implies Q, then it's logically equivalent with not Q implies to not P. Then to prove this law, we need to get P implies Q and not Q implies not P, and check if they are similar. So to get P implies Q, I think we already get it many times. But another time, I emphasize here that if you have both sides true, then it's true. If you have P, which is the hypothesis, okay, false, then also the result is true. If P, which is the hypothesis, false, true, sorry, and the conclusion false, it's the only possibility that you have the result as false. Okay, now to get this also table, you need to, okay, let me clear it more. We have P, Q, not Q, and not P. Then we get the result. P, Q, P, true, true, false, false, Q, which is a true, false, true, false. This is all possibilities. Now, not Q. I will bring Q first because it's the first term in this implication. So, not Q, which is here true become false, false become true, true become false, false become true. Now we have not P. Not P, here P, true become false, true become false, false become true, false become true. Now I need to get not Q implies to not P. The result will be, because this one false, the hypothesis false, then the result will be true. The hypothesis is true, I will look to conclusion. It's false, then the result false. This one false, then the result true. Both true, then the result true. You look to this one and this one, you will find it's identical. Then we proved this law, contrapositive. Now we have this laws. I think most this law very famous in mathematics, even in normal mathematics. Some laws, because it's from logic, some logic law, maybe you don't know it before, but some I think already familiar for you. We have this identity law. Identity law mentions that if we have P and T, T means true. It's logically equivalent to P. Or in another term, the side that will define the value of this operation will be P. Okay? Let's check the truth table here. Because I have one proposition, then what is the possibilities that it could be true or false? Okay, then I will make P and true. Okay, P here, true. True and true will be true. P here, false. False and true will be false because we have an operator. So P here, it's define the result. That's why this operation or this compound proposition logically equivalent to P, because P here will give you the result. Same thing if you make P or false. Here P will give you the result. If P true, then P or false will be true. If P false, then P or false will give you false, then will give you the value of P. Okay, this is the first law, identity law. This means P will identify the result. Okay, if we have and, or with the false. If we have and with the true, also P will identify the result. Domination law. Domination law, it's also similar, but here, if I have P or T, the result will be true. If I have P or false and false, the result will be false. And it's logically, we mentioned that if we have or operation, if any side is true, the result will be true. So it doesn't matter P here. If we have or and one side is true, then it's logically equivalent to true because the result will be true. If we have P and false, P here doesn't matter. The result will be false because we mentioned that for AND operator, if any side false, the result will be false. So it's come from here, from this idea, this law. Okay. Idmo potent law. It's in short, if you have P or P itself, the result will be P. If you have P and P, also the result will be P. So if it logically equivalent with P. So P and itself, it's logically equivalent to P. P and itself, it's logically equivalent with P. And it's very simple to understand it because if P true, then true or true will be true. If P false, false or false, sorry, will be false. Here's something, true and true will be true. This same value of P. False and false will be false. So it's a simple one also to prove it. Double negation. And it's very famous rule. In anything, the negative of the negative become positive. It's famous rule in mathematics, in life, in anywhere, that positive of or negative of the negative will be positive. Then double negation rule or law said that if we have negative of the negative, then of P, it's logically equivalent with P itself. It's simple to prove it. If we have P, we have the possibilities true and false. Okay, not P will be false, true. Another time, not P, the result will be here, false become true, true become false, then it's P again. It's logically equivalent. Okay. Commutative rule, P or Q, it's same if you put the Q first, Q or P. Similar for and if we have P and Q, it's same if we put the Q first, become Q and P. Because if you have truth table, okay, it doesn't matter if you take P first and Q or Q and P or Q or B, P or Q. You will get same result. Okay, associative rule, we already mentioned it here or before 2 slides. When one student asked me about this thing, he said, if I have P and Q and R, so you can associate any two of this with each other. You can associate P and because you have same operator here. Okay, if different, it become distributive law. Here it's associative law. P and Q, you can take it, then you make and R, or you can take Q and R, then and P. You can take any two proposition here first, then make the other operations. Then this is associative law. You can take here P or Q. You can take P or Q R between the brackets here, or this, because we have same operator. For the and, similar. If we have and operator for all the sides, you can take any two sides with each other, then the result will be with the third operator. Distributive law, I think we already mentioned it. De Morgan law, we already mentioned it. You can distribute this not operator for the or and for the and, but or become and after distribute this not, and become or after distributing this not operator. Observation law as this. Look, if you have P or, okay, P and Q, the result will be, or it's logically equivalent to P. Okay, of course, when students will mix between this one and this one, it's totally different. Here, I have between the brackets Q and R. Then you have here 3 different propositions. But here I have 2 propositions. P and Q. So when you want to distribute this P using OR, here inside the result will be P only. And if you distribute this AND operator for OR operator and one side it's same like the outside, then this outside will be the result. You can prove it using truth table very easily. So this observation like it's this P observed this Q and the result will be only P here. But you need to focus. These two different operator here, or then here and here and then here or, and one side it could be this one or this one. It's same like distributed one, the outer one. Okay, this observation law. We have also negotiation law. This negotiation law said that if I have P or not P, it is equivalent to true. If we have P and not P, it's equivalent to false. And proving this, it's very easy. What's the rule for OR operator? If I have any side it's true, the result will be true, yes? So we have, if this side true, this side false. If this side false, this side true. Then I have one side true, then the result will be true. Similar, we can prove this. Okay, what the AND operator said, if I have two sides true, the result will be true. But if any side false, the result will be false. So I have the proposition and its negation. This means if this is true, this false. If this false, this is true. So always I have one side false, then always the result will be false. Okay, this is the negation law. We will take some example to make some logical equivalent proof using this laws, but let's take more laws. Okay, this law, all these laws, okay, you can understand them from our previous section, okay, our previous lecture, because I think we already mentioned this one. If you have P implies Q, it's equivalent to not P or Q. Not P or Q. Okay, it's good. This one, the opposite for this one almost. Yes, this means this one come from this law, come from this law. If you have P or Q, it's logically equivalent to not P implies to Q. So it's better to connect between the laws. Okay. This law, it's like negation law, but for the implication. We already mentioned it before. If you have P implies Q, then to make negation for it, you have to, okay, take the opposite. Not Q implies to not P. It's logically equivalent. Okay, then P implies Q, logically equivalent to not Q implies not P. Okay, we have another law here. Mentions that P and Q, it's logically equivalent to not P implies not Q. And we have more laws, okay? I think we will use this law if it's come with us during the examples. If not, we will not using it too much, because we can also each of this law we can prove it using truth table also. So I think until here will be enough for us. If we need any of this law, we will return to it from our examples. And if I bring in the exam, okay, a question that need this laws, I will put it in the equation. Okay, so I think until here enough for this laws. If we need this, I will give you this laws. I think most important, this part, you can understand it and use it. This law, I already give it to you. This equivalent for bioconditional statement, I mentioned it before. If we have P bioconditional with Q or double implication with the Q, this means it's equivalent to P implies Q and Q implies P. You take the two sides, yes? The two sides. P, Q implies P and P implies Q. Okay, this is a clear one. We already mentioned it before. Here, similar for this one with implication, but the different, it doesn't matter if you put P, it doesn't matter if you put P double implication with or double implication or bioconditional with the Q or Q double implication with P. It's similar, okay? It's equivalent actually. That's why if you make not for both, you don't need to make Q first, then P second. It doesn't matter. So P double implication with the Q, it's equivalent to not P double implication with not the Q. Okay, same thing. I think we can use until here. Okay, here we can use maybe until here. Okay, Now we have some examples here for proof equivalence. Okay, we will take a break for 5 minutes. It's the time for the break. We will take a break for 5 minutes. 5 minutes break. Okay. Okay, we return again. How many students around? Raise your hand, please. Okay. Okay, we continue. Okay, we have first example to use this laws to improve logical equivalent. So we can prove logical equivalent using two ways, truth table, or we can use equivalence law. Okay, now we will use equivalence law or logical equivalence law to prove this logical equivalent proposition or compound proposition. It's said that if we have this one, not between practice P or not P and Q, it's logically equivalent to not P and not Q. This is not rule. This I give you this proposition and I said I need from you to prove that this both sides logically equivalent. So we need to start from first side and reach second side. Okay. Simplest way to do this that if we have like this practice and not, and we have practice, we try to make or use the rules. First, we need to distribute this not and distribute this or for this practice, and then we can see later what will happen here. So if we apply Morgan law here, so we have not and we have consider this part. It's much easy if you ignore what inside now. Consider it's R. Then we have this one as like this, not P or R. Using De Morgan law, we can distribute this not inside. So we can make not P and not R. So we use this law, De Morgan law, here. When we distribute not on or, we can distribute it, but not and become or and or become and. Okay. So now what is R? R, it's here. Let me now just Now we have not P and not, what is R? It's here, this one, not P and Q. So at the beginning, it's better to consider, for example, this one, this part, consider it as R, then apply the rule, then you give the result of R. So using the De Morgan law, we can distribute this not for this brackets and this or become and like this. So we distributed it, not P and not all this. This become here. So now we have ignore this not P. We have side and we have practice here with or. So we can use De Morgan law, and we can use double negation law for this one. Sorry, I go to the next step directly. I speak about this one. Okay, we have first not. So we want to distribute it inside using De Morgan law. So this side, take it here. If we want to solve this part, not P and not Q. This after we used, sorry, no practice. After we used, or we can use this practice. This after we used De Morgan law. De Morgan law. What is De Morgan law? Not P and Q. It's become not P or not Q. Sorry, here or. Okay, here first part not, and this or this and become or, and this the second part also takes the not inside. Now we have not, it's become without not because the double negation. If you have double negation, you can remove it because first not takes the second not. So like this, not P, we can remove it and put only P. So this part become P or not Q using De Morgan law and double negation law. Okay, now if you look to this one, you have and between brackets you have or. Doesn't matter what around this sides. So you can distribute this inside using distributivity. Yes. So first side and first side inside, outside and first side, or outside and second side. Here, what I have outside and first side here, or I distributed this here, not P and not Q. Okay, this using distributivity. law. In this side, we have this law, P and not P, always false. Yes, P and not P. It doesn't matter to write P and not P. It's similar if you write not P and P. And the result always will be false, because the proposition and its negation or negative always false. So I can remove this part. Sorry, where is the pointer? Here. Okay, I can remove this part and put false. And we continue. And this part. Okay. Here, false or anything. The rule said R or false, it's equivalent to R. B or false, it's equivalent to P. It's identity law, yes? A Q or false, also Q. Why? Because this side will identify the result here, not the false, if you have OR operator. So, false or this side doesn't matter what inside it. I don't know what inside it. The result will be always this side itself. So I get this one as the result. If you check, we reach the other side, then we proved what we need here. So to prove this equivalent or logical equivalent, you need to start from this side and reach the other side using the laws. De Morgan law, distributivity. I think distributivity and association rules and even identity rule very clear. De Morgan law also you can understand it. Double negation, the positive, the negative of the negative will become positive. Then two negatives will eat each other. Okay, it's very clear. Just you need to practice with some examples here. Another example, we need to prove that this side logically equivalent with this side. Here we need some preparation. Okay. We have here note that from this implication, we need in the right hand side, this one. This right hand side, we can write it like this. We mentioned before that P implies Q. It's equivalent to not P or Q. Here's the law. You see the law? P implies Q. It's equivalent to not P or Q. Okay. Then we can write this side, or if we reach from the right, this means right hand side. If we reach in the right hand side, not P or this the other side, Q and R, it means we reach the result. Here I know some students will have some confusion. Why? Because we have here Q and R. Consider it, for example, L. P implies to L, it's equivalent to not P or L. Now remove L from here. You have, instead of L, Q and R. Okay. Then to reach this one, I need to reach this one. This is the law. Okay. So we start from the left hand side. This means here. To reach this right hand side, to reach this one. If we reach this one, then we reach this one. Okay, let's start. This is the left hand side, LHS, this means left hand side. This one. Look to this one. First, if you have implication, first thinking, if you have implication, you need to change it to and or something like this. So we can use substitution law. This name of this law, substitution law. We can use substitution law twice time. Why twice time? Because we have here implication and implication. This one as it, and this side and this side. This side, P implies Q, become not P or Q. This side, P implies R, become not P or R. So this is the result after apply the substitution law for this one and this one. Okay. Now if you look for these two laws, it's become from this. It's become, you look to this side, it's become from, if we distribute not P, okay, or Q and R. This its origin. We can return it to this origin using distribution law. How come? If you look here, P distributed here inside, not P or Q, not P or Q, and we distribute it, not P or R. In another term, to focus here, you see these laws, we mentioned logically equivalent. This means this side equivalent to this side and this side equivalent to this side. So you can come from this side to this side like this, or the opposite. So you can distribute, for example, in this distributive law like this, or you can make the opposite. If you have the distribution, you can reach this one. So here, same idea. We have the distribution first, then we gather this B. We take it as the common part. It's a common part, actually. It's here and here, and have same operation, which is OR. Then what remain here inside? Q and R. Okay, then we reach this one using distribution or distributivity law. Now it's, you look here, it's what we need. If we reach this one, then substitution law, which is the first one we applied here, okay, for the implication, said that we can reach P implies to Q. You can imagine this one L, okay? If you have not P or L, it's logically equivalent to P implies to L. So if this L, then we can make it like this, implication. So, or become implication, and we remove the negative from the first part. And that's all what we need. This is the right-hand side. So we reached from left-hand side to right-hand side, then it's done and it's improved. Okay, it's improved here. We have more examples. Which file? Lec2. I think this one. Okay. We have more examples here. I think I need to close it and make it again. Okay. More examples. This example asks you not to prove, ask you to show that, let me change the color only. To show that this one or this compound proposition is a tautology. I need one of you to answer me. What's the meaning that this proposition is a tautology? What this mean? Shows that this proposition is a tautology. Okay, very good. This means it's always true. Or in another term, I need to prove that this proposition logically equivalent to true. So if I start from this proposition, I need to reach true. Good. I'm happy that many of you focus with us and answer. So this is the meaning of proof or show that this proposition or compound proposition is a tautology. This means I need to start from it and reach it true, or in another terms that it's logically equivalent to true. If it's logically equivalent to true, then I proved this. It's a tautology. Okay, so we can do this using two ways. First way using the law, second way using truth table. So maybe sometimes I will ask you to answer using truth table. Maybe I will ask you to answer without a truth table. If without a truth table, then you need to use the laws. Like De Morgan law or association law or negotiation law, double negation law. Okay. If I did not ask you, then you are free to use truth table or logical equivalence law. So if it's not mentioned clearly, you are free to use anyone. So we will take one example using the laws and one example using the truth table. Okay, then we need to start from this part and reach true. Okay, starting from this part, I said for you, what is the first step if you have implication in your left side? The first step should be remove this implication. How to remove implication? We have simple law. If we have P implies to Q, then it's not P or Q. Then we have this side implies to this side, then the result will be first side was not or second part. Then this using this rule. Okay, if you forget the rule, you can, especially in the improve. Okay, for implication, if you forget the name of the rule, you can write it like this. Because I have this rule. S implies R, logically equivalent with not S or R. Okay. Now, if you look here, we have not. Always, if you have not and you have practice like this, you need to get it inside. And De Morgan law said, if we have not and practice like this, for example, S or R, then you can distribute it inside. It become not S and not R. If you have not for practice S or R, you can also distribute it inside, not S, but this and become or not R. This De Morgan law, very simple. Okay, then I distribute this inside and this and become or, not P or not Q. They remain as it. I just put it as it here. Okay. Then if you look to this one, all have or. So you can use associative rule and commutative law. You can bring any two with each other. You can bring one before the other one. Why? Because they have the same operator, which is or. If they have all and, also you can do this. So because I have law that not B or P always equivalent to true, I need to bring like this, not P with P, not Q with the Q, to reach this true, okay? So I just reorder this part, just reorder here, just reorder because all have this or. So I put P with not P and Q with not Q. So I have P or not P or Q and not or not Q. Of course, you can remove the practice, but I need the practice to use the negation law that if I have Q or not Q, the result will be true. If I have P or not P, the result always true. Now, domination law said if you have any part of the or true, then the result will be true. Even if you did not write domination law, it's very clear that for the or operator, if you have any part true, the result will be true. Then we reach here, we reach what we need. It's logically equivalent to true, then it's a tautology. Okay, another example, last example. Sorry, I know maybe I get a few minutes more than our time. So just this last example, it's very quick example. This example mentions that, shows that this proposition is a tautology using truth table. Now we need to use truth table. Let me just here remove the answer and answer it very quickly with each other, because I think we become very familiar with this truth table. Okay, then we need to use truth table to prove that this one is a tautology. This means if all the possibilities of this one true, if it's always true, then it's a tautology. Okay, we start. We have only P and Q. This all possibilities for P and Q. True, true, false, false, true, false, true, false. Okay, now first term is not P. I bring not P here. P, not P. This means true become false, true become false, false become true, false become true. Now, the other side here, P or Q. P or Q, also this two side. What's the rule of the or? Or said, if any side is true, the result will be true. This means true and true, true, true and false, true, false and true, true, false and false, false. Okay, now we need to make and between these two parts here, not P and P or Q, these two parts. I know it's finished, okay? Just, I know time up, just 1 minute, just 1 minute. We already finished here. The result of this and these two parts, and if two sides is true, the result will be true. This is the only two-sided true. All other will be false. Now we said implies Q. All this implies Q. Okay? All this implication with the Q. I will copy this Q again. Only this Q, I will copy it again to make it easier to find the result, which is true, false, true, false. Now this two-side implication said, if two-sided true, the result is true. I have any two-sided true? Yes, this one, two-sided true, the result is true. And it said, if first side false, the result is true. This false, then true. This false, then the result is true. This false, then the result is true. If you look here, all the result is true. It's always true. Then it's a tautology. Here you can see in the book the exercise 9, 10, 11, 15, and exercise from 16 to 33 at page 35. I advise you to answer these exercises and previous exercises that I give to you. Okay, that's all. Thank you for attending the class, and sorry for take more times. See you inshallah next week. Have a nice weekend, and Assalamu alaikum. Guru Shuruz.